Today, I'm going to present a novel cross-consistency-based semi-supervised approach called cross-consistency training, which was introduced in CVPR 2020. In semi-supervised learning, we have a small number of labeled dataset and a very large set of unlabeled dataset. This setting could be useful especially when labeling data is expensive. The objective of this semi-supervised learning is to exploit the larger number of unlabeled examples to train a network and to perform well on the test data drawn from the same distribution as the training data. Several famous methods have been used to tackle this problem, but the recent progress in semi-supervised learning was confined mainly to the classification tasks, and its application in semantic segmentation is still limited. Recent approaches in semi-supervised semantic segmentation includes the work with weakly supervised approaches and generative adversarial networks adapted to semi-supervised setting. So among various methods used for semi-supervised learning, consistency regularization encourages a model to produce the same prediction when the input is perturbed. So recently, CalMix used mix-up to enforce consistency between mixed outputs and prediction over a mixed input. There are several assumptions in semi-supervised learning, and the effectiveness of consistency training depends heavily on the behavior of data distribution, which is related to cluster assumption here. Cluster assumption states that decision surfaces should lie in low-density regions, not crossing high-density regions. As semantic segmentation is a pixel-wise classification problem, cluster assumption may not hold with most of the pixels. That is, similar spatial semantics not necessarily reflects the same class. Previous work published last year showed that this cluster assumption does not hold in input space. Like the experiment done from previous work, authors measured the average Euclidean distance between neighboring patch from input space and representation level to examine the local smoothness. They observed that for semantic segmentation, the low density regions are more apparent within the hidden representation than within the input. This finding motivates their approach where perturbations are applied to the encoder's output rather than the input. Here they consider a shared encoder and a main decoder that are trained using the labeled examples. To leverage unlabeled data, they then consider multiple auxiliary decoders whose inputs are perturbed version of the output of the shared encoder. The consistency is imposed between the main decoder's predictions and that of the auxiliary decoders. CCT differs from CalMix I introduced before, as CCT introduces perturbations in the output of the encoder rather than input. Also, it doesn't need multiple forward passes and easy to be adapted to other settings, which is not for CalMix. Here's the total loss as combination of supervised cross-centricity loss and omega U weighted unsupervised loss. And with various perturbation settings, they generate K perturbed version of the intermediate representation so that each perturbed version is to be fed to the K auxiliary decoder. The training objective is then to minimize the unsupervised loss, which measures the discrepancy between the main decoder's output and that of the auxiliary decoders with mean squared error distance measure D here. To exploit the weak labels, authors added a classification branch. They start by generating class activation map and pseudo pixel level labels where foregrounds and backgrounds are thresholded with attention score. This is the result. They first performed the ablation studies to see the effect of the number of auxiliary decoder and the number of perturbations included. Overall, there was a significant gap between each of the perturbations used here, which confirms the effectiveness of enforcing the consistency over the hidden representations. This work outperforms previous work relying on the same level of supervision and even methods exploiting image level labels. The authors measured effectiveness of CCT when applied to multiple domains with a variable degree of labels overlapped on cityscapes and Cambridge dataset. Also, for disjoint cases, they used cityscapes and sun dataset. During training, they alternate between two domains drawn from different distributions and finally achieve better performance compared to the baseline while delivering similar results on each of the settings respectively. So this is the summary of this work. For the remaining future work, other perturbations can also apply to this work. Also, this work can be applied to other learning settings or visual tasks. This is the end of the presentation. Thank you for listening.